So if omega 1 equals omega naught, so now our equation looks like d squared plus omega naught squared, the natural frequency y. But this time the driving frequency, the input frequency, is omega naught itself. Then the same analysis, you know, a lot of it is well, no, I better be careful. Better be careful. Let's go through the analysis again very rapidly. What we want to do is first complexify it and then solve. So the complex equation will be d squared plus omega naught squared times y tilde equals e to the I omega naught t this time. But now I omega is a zero of this polynomial. That's why I picked it, right? If I plug in I omega 0, I get I omega 0 quantity squared plus omega naught squared. That's 0. So I'm in the second case because, so I omega naught is a simple root, simple 0 of d squared plus omega naught, that polynomial squared. Therefore, the complex particular solution is now t e to the I omega naught t divided by, well, divided by p prime where you plug in that root, the I omega naught. Now what's p prime? P prime is 2d, right? If I differentiate this formally, as if d were a variable, the way you differentiate polynomials, the derivative, this is a constant, and the derivative is 2d. So the denominator should have 2 times, for d, you're going to plug in I omega 0. So it's 2I omega 0. And now I want the real part of that, which is what? Well, think about it. The top is cosine plus I sine. The real part is now going to come from the sine, right? Because it's cosine plus I sine. But this I is going to divide out the I that goes with the sine. And therefore, the real part is going to be t times the sine this time of omega t, naught t. And that's going to be divided by, well, the I canceled out the I that was in front of sine, the sine function. And therefore, what's left is 2 omega naught down below. So that's our particular solution now. Well, it looks different from that guy. It doesn't look like that anymore. What does it look like? Well, it shows, the way to plot such things is basically it's an oscillation of frequency omega naught, but its amplitude is changing. So the way to do it is, as always, if you have a basic oscillation which is neither too fast nor too slow, think of that as a thing, and the other stuff multiplying it, think of as changing the amplitude of that oscillation with time. So the amplitude is that function t divided by 2 omega 0. So just as we did when we talked about damping, you plot that and it's negative on the picture. So this is the curve, the function whose graph is t divided by 2 omega naught. That's the changing amplitude, as it were. And then the function itself does what oscillation it can, but it has to stay within those lines. So the thing that's oscillating is sine omega naught t, which would like to be a pure oscillation, but can't because its amplitude is being changed by that thing. So it's doing this. And now the rest I have to leave to your imagination. In other words, what happens when omega naught is equal, when the driving frequency is actually equal to omega naught, mathematically, this turns into a different looking solution, one with steadily increasing amplitude. The amplitude increases linearly, like the function t divided by 2 omega naught. Well, of course, this is not realized in real life. The amplitude can increase linearly up to a certain point, but you know, the swing gets to there and the little kid says, stop, I'm scared. Uh, or the bridge falls down and that ends that, or whatever. But this is, this is an important phenomenon of everyday life. I keep thinking of the, I've forgotten what order these happen, but when the Green Building was built, it was that was a skyscraper for MIT. It's still MIT's skyscraper, more or less. This being the building for that housed the Earth and Planetary Sciences. At that point, it was called Earth and Atmospheric Sciences. The wind set up vibrations because the building resonated just the wrong. If the wind was just at the right frequency, that produced little vibrations, and a lot of the windows fell out. Well, that was fixed by getting thicker glass. They adjusted, calculated it all, and then they built the John Hancock Building across the river, or maybe it was the other order. I've forgotten which. But the skyscraper with, I think it's still the tallest building with all glass. No, I think they built big. Anyway, with all glass paneled windows, the whole beautiful building, all of glass. And the wind, when it was just the wrong velocity, or just the right velocity, set up resonant vibrations, and 1/3 of the windows fell out. I think the architect was the same, but it was probably the engineers who were different. And I have nothing against engineers, but I'm sure there were ads by Remainder. There were ads in the papers from Building 19, which was a not an MIT Building 19. There was a thing which sold leftovers from various projects of remaindering, except it didn't remainder books, it remaindered everything. And big ads appeared. We have these beautiful panes of glass that will make wonderful coffee tables. We can't tell you where they came from. I think all the windows probably had to be replaced. So anyway, that's bad resonance. But there's good resonance too. There's the good resonance, which enables us, with all the signals from all the TV stations and radio stations floating around in the air, what enables us to pick out one particular signal from all those is by resonance, by getting something in the little set which is tuned, adjust the tuning to that particular frequency so that only that frequency makes the radio or the TV do its thing, and then that's the station one gets. So that's pretty rough. Well, my point is only that this is an absolutely basic phenomenon for good and evil, physically, and B, it corresponds physically to an oddity in the solution of this differential equation. It's a second-order differential equation in which something peculiar happens when this thing is a root of the characteristic, is a characteristic root, a root of the characteristic polynomial.